Hey, Math 20-2. Today we're going to look at some measurement. A little review and preview from grade 10. All right, in the previous math course we learned to convert within and between Systems International and the imperial system, so metric and imperial. These conversions were done using one of the following three methods. Either using the metric unit chart as a number line, or we could use proportional reasoning, or we did unit analysis. So in this lesson, we'll do a basic review of these methods and also introduce the concepts of accuracy and precision in measurement. So recall the following charts used for conversion. These will be on your, or something similar will be on your formula sheet. Not this one, this is pretty basic. The metric number line. This is an in-depth one. Here's a pretty simple metric number line. All right. Conversion within and between metric and imperial. So this will be on your formula sheet. You'll have that with you at all times. All right. So let's look at a few examples then. Using the metric unit number line to convert within the metric system. So the neat thing about the metric system is they're related by factors of 10. So as such, if we're going to convert between metric units, we need to know how many positions on the number line we have to move. Each movement of one position represents a power of 10. For example, to convert from kilometers to centimeters, we move 5 positions to the right. So 1 kilometer is 10 to the 5th, 5 powers of 10, or 100,000 centimeters. To convert centimeters to kilometers, we move 5 positions to the left, so 5 powers of 10, but now we're going to the left, so that's a 10 to the negative 5. So 1 centimeter is 1 over 100,000 kilometers, or we could say 0.12345 kilometers. All right. So use the metric number line to complete the following. I would like you to do that real quick. Just pause this recording and try these 4. Make sure you get them right. Then you can start it up again. All right, so we look at example A, 1 meter to centimeters. That means we have to move meters to centimeters is 2 units to the right. So I take 1 meter multiplied by 10 to the exponent 2 powers of 10, which gives me 100 centimeters. 2.3 liters to milliliters. Again, we're going from liters to milliliters. We're going to move 3 positions to the right. So I take the 2.3 liters multiplied by 10 to the power of 3, or 3 powers of 10, which is 2,300 milliliters. 750 centimeters to meters. I'm going to have to move centimeters to meters. That means I'm going to move 2 positions to the left. So I take 750 centimeters multiplied by 10 to the negative 2, gives me 7.5 meters. And finally, milligrams to kilograms. That's 6 positions to the left. So I take the number of milligrams I have multiplied by 10 to the negative 6, 6 powers of 10 to the left, and I figure out how many kilograms I end up with. All right, so that's using the metric unit number line. Using proportional reasoning to convert. In order to use proportional reasoning, we need to know one of the following: a commonly known conversion or a ratio given in the question. As in previous math courses, set the ratio in this form. So you need a fraction equaling a fraction. There are a number of ways of setting out the work for proportional reasoning. Whichever method is used, it's essential that the units are equivalent in each ratio. All right? So we'll have a look and make sure we set the proportions up properly. Example 2, slideshows at collectibles. Slideshow collectible stories considering making a statue of a dinosaur. They're considering a scale whereby 1 centimeter represents 2.1 feet. The height of the statue of the dinosaur will be 12.5 centimeters. What's the actual height of the dinosaur? So we're given a scale. Let's start with that. 1 centimeter is 2.1 feet. That's the scale we're given. We were told that the height of the statue will be 12.5 centimeters. So that's going to stay on the same line as the centimeters. We're going to figure out what's the actual height of the dinosaur, find out x, how many feet tall that is. So I've got my proportion set up. I've got consistent units, centimeters over feet, centimeters over, when we figure out what x is, that'll be in feet. So I cross multiply 1 centimeter times x, so I've got 1 times x equals 2.1 times 12.5. All right, and then I divide both sides by 1, and we come up with x is 26.25. And that's in feet. All right. So answer the question. The dinosaur would be 26.25 feet tall. Use proportional reasoning to convert 0.05 miles into inches. So you want to go to your chart from the last sheet from first page there, or on your formula sheet, and we know a commonly used conversion from miles to feet. All right, so let's do that one first. 1 mile is how many feet? 1 mile is, look on the chart, 5,280 feet. We want to turn this question is 0.05 miles is how many feet? So first we'll change miles to feet, and then we can change feet to inches after that. All right, so let's solve for x. Again, cross multiply. 1 times x is going to equal 5280 times 0.05. So we find out that x is roughly 264 feet, 0.05 miles. And now we can do another proportion. So we've got 1 foot is 12 inches. We know that conversion. If you look on the front page, 1 foot is 12 inches, or your formula sheet. We're now told 0.05 miles is the same as 264 feet. How many inches is that? Maybe we'll call that y. So now we cross multiply. 1 times y will equal 12 times 264. So 12 times 264, that's about 3,168 inches. All right, so we have converted 0.05 miles into 3,168 inches. That's using proportional reasoning. We had to do 2 different proportions. All right, first from miles to feet, that's what x was, and then from feet to inches, that's the final answer. All right. Using unit or dimensional analysis to convert, when several changes of unit are required in a conversion, a different process called unit analysis is often used. No, proportional reasoning can be used when several changes of units are required, but we must do it several times to complete the conversion. So just like we did last time, we had to do 2 different proportions to get there. All right. In unit analysis, if only one conversion is required, the basic setup is, in this approach, is given. Required equals given times the conversion, with units being placed properly in the numerator and denominator. If it's done correctly, as in proportional reasoning, the unit left over is the unit required in the answer. So let's consider the process of converting 3.5 kilometers to millimeters using unit analysis. We would first convert kilometers to meters. So we're given the original measurement, 3.5 kilometers over 1. That's our original. We're then going to convert meters to kilometers. All right, kilometers to meters. So remember, I want to get rid of my kilometers, so my kilometers should end up in the denominator of my conversion. So 1 kilometer is 1,000 meters. And then I convert meters to millimeters. So to get rid of this meter, I must put the meters in this denominator. And if I do my conversion now and go ahead and multiply across, I'm only left with millimeters, right? So 3.5 times 1,000 times 1,000, just like it says, all divided by 1 times 1 times 1. Well, it's dividing by 1. And the only unit we have left is millimeters. Everything else has been reduced out. All right. So in class example, we used proportional reasoning to convert 0.05 miles to inches. What conversions will the student need to consider to solve this problem using unit analysis? Well, they have to know the conversions from miles to feet, the conversion from miles to feet, and the second conversion from feet to inches. So if you know those two conversions, we can use unit analysis. So we start with what we're given. We're given a measurement of 0.05 miles. 0.05 miles. Put that over 1. Multiply. Multiply by the conversion of miles to feet. So if I want my miles to get canceled out, I want to put my miles down here in my denominator. That means the feet have to go up here in the numerator. So we know your conversion from the formula sheet. 1 mile is 5,280 feet. So 1 mile is 5,280 feet. And now I want to convert feet to inches. So again, feet are in my numerator. I want to put in my conversion the feet in the denominator. Therefore, inches must go up in the numerator. And we know from our formula sheet that 1 foot is 12 inches. So now we can go ahead and multiply this out. 0.05 times 5280 times 12. So 0.05 times 5280 times 12, all divided by 1 times 1 times 1, which is 1. And we've got our conversion. Let's eliminate the units. So I've got a mile in the numerator, a mile in the denominator, they're gone. A foot in the numerator, a foot in the denominator, they're gone. My final unit then should be in inches. And then it's just a matter of calculator work. 0.05 times 5280 times 12 gives us the same answer we had earlier, 3,168 inches. All right. So unit analysis, we can do multiple conversions all in one straight conversion statement. Example 5. A physics student was required to convert an answer of 75 meters per second into kilometers per minute. What conversions will a student need to consider to solve this problem using unit analysis? Well, we want to go from meters to kilometers. They need to know that conversion. All right. Meters to kilometers. And then we want to go from seconds to minutes. So you need to know that one as well. Seconds to minutes. So those are the two conversions they need to know. All right. Now convert the student's answer of 75 meters per second to kilometers per minute using unit analysis and show the cancellation in units. Here we go. What are we starting with? 75 meters in 1 second. We want to convert then meters to kilometers. So I want to get rid of the meters, so I put my meters in the denominator, and you keep your kilometers in the numerator. So we know that 1 kilometer is 1,000 meters. That's that conversion. Now let's convert seconds to minutes. Again, seconds are in my denominator over here, so I want to put seconds in my numerator to get rid of those. Therefore, minutes must go in the denominator. And we know that 1 minute is 60 seconds. All right, so once we have it set up properly, we can figure out how many kilometers per minute we need. All right. So I go ahead and multiply then. 75 times 1 times 60. Multiply all your numerators. Divide that by 1 times 1,000 times 1. And let's look at what units we have. Well, a meter in this numerator, meaning that meter in that denominator cancel out. A second in this denominator and a second in this numerator, those cancel out. That means I'm left with, in my numerator, I've got kilometers. In my denominator, I've got minutes. So kilometers per minute. So now it's just calculator work. 75 times 60 divided by 1,000 gives us 4.5. And our units are kilometers per minute. All right, so that's using unit analysis. Great, we're going to keep going. You can do your work in a minute. Let's do a little quick review on slope. We're also going to use the concept of slope. Steepness of a line is a definition of slope as a rate. So slope is a rate. We will review basic concepts of slope. Recall that the definition of slope is rise over run. Our symbol for slope is lowercase m. If you're given 2 points on a coordinate plane, then rise is a difference in the y-coordinates, y2 minus y1. Run is a difference in the x-coordinates, x2 minus x1. So let's consider the line segments A, B, and C, D as shown. Determine the slope of each line using the formula m equals rise over run. So slope of AB equals, well, from A to B, that's a rise of 3 units and a run of 1, 2, 3, 4, 5, 6. So you got a rise of 3 over a run of 6, which means you've got a slope of 1/2 if we put that in lowest terms. Slope of CD, well, from C we're not actually rising to get to D, we're actually falling. So if we're going to fall 3 units, we're going to run 1, 2, 3, 4 units. My rise is 3, my run is 4, but I'm not really rising to go from C to D, I'm actually falling. So that's actually a negative slope. Lines that fall to the right or rise to the left are considered negative sloped lines. So that slope is 3/4. If we use our formula, it takes that idea of positive and negative slopes into account, and the formula will automatically calculate that. So the slope of AB and the slope of CD, well, we need to know the coordinates of these points then. So slope A is located at 1 and 8. So the coordinates for A are 1 and 8. The coordinates for point B are at 7 and 11. So let's use our slope formula. I could identify these two coordinates as x1, y1 for point A, x2, y2 for point B. And then when I substitute into my formula, substitution is pretty quick. So slope of AB, y2 is 11 over, minus y1, which is 8, over x2 minus x1 for our run, 7 minus 1. So 11 minus 8 is 3, 7 minus 1 is 6, 3/6 is the same as 1/2, so we got the same slope. Very nice. If I want to find the slope of CD, again, we must know the coordinates of these 2 points. C is located at 6, 5, and D is located at 10, 2. So we can plug into our formula. y2 minus y1, y2 is 2, y1 is 5. 2 minus 5 over x2 minus x1, 10 minus 6. So 2 minus 5 is a negative 3. 10 minus 6 is a positive 4. Slope is the same. That formula takes into account positive and negative slopes. Does it matter if the slope in B is calculated using the 2 endpoints of the line or 2 points found anywhere on the line? Explain. Slope of a line is consistent. Therefore, you can pick any 2 points on the line. All right. Example 7, complete the following statements then. Slope is a measure of the steepness of a line. Slope is the ratio of the vertical change, called the rise, over the horizontal change, called the run. A line segment which rises from left to right, rises from left to right, so it's going like that, has a positive slope. And a line segment which falls from left to right, so it looks something like that, has a negative slope. A horizontal line segment like this, has no steepness, so there is no rise, but there's lots of run. That has a slope of 0. And a vertical line segment, which would look like this, has a lot of rise, but no run. So we're dividing by 0. Anytime you divide by 0, you get an undefined statement. So the slope is undefined if you have a vertical line segment. The slopes of all line segments on a line are equal. The slope of a line is consistent, so it doesn't matter where on the line you pick points to figure out the slope, it will work. And let's quickly look at accuracy and precision. All measurements contain a degree of uncertainty, and so there is no perfect measurement. To minimize this degree of uncertainty in a measurement, there are two concepts to consider when choosing a unit or a tool in taking a measurement. Those two concepts are accuracy and precision. So they're two slightly different things. Let's understand the definitions. Accuracy indicates how close a measurement comes to its real value. The smaller the difference between the measurement and its accepted real value, the more accurate the measurement is. The accuracy of a measurement can only be as accurate as the measuring device used. All right, so that's accuracy. If you look at precision, there are two aspects to precision in measurement. In a single measurement, precision is determined by the number of significant digits used to express the measurement. This in itself can be influenced by the measuring instrument used. The smaller the unit used to measure with, the more precise the measurement can be, as given by that example. Precision also refers to the ability of a measurement to be consistently replicated, i.e. indicates how close a set of measurements are to one another using the same measuring device. So consistencies also measure precision. So to have high precision, you must be able to consistently replicate results and to measure with as many significant digits as possible. Let's look at example 8 then. Two students are asked to measure the width of a cupboard that is known to be 1 meter wide. Beth gives the measurement as 39 inches, and Deshawn gives the measurement as 37.55 inches. Which student's measurement is A, more accurate, and B, more precise? So if we're talking about accuracy, who's closer to the given actual measurement? Well, obviously Beth is at 39 inches. That's closer to 39.37 than 37.55 is. Who's more precise? Well, Beth gave hers to the nearest whole inch. Deshawn gave his to the nearest hundredth of an inch. So Deshawn is a more precise measurement. It's not as accurate, but it is more precise. It is possible for a measurement to be accurate and precise. It could be accurate and not precise. It could be precise and not accurate, or it could be neither. Each of these are illustrated in the next example below. Dash throws 4 darts at a dartboard, where the goal of the game is to throw as many darts as possible in the center of the board. His first 3 attempts are illustrated below. Figure 1 has all 3 of the darts right about here. Figure 2 has all 3 of the darts very close to the center. And figure 3 has darts all over the place, 1, 2, 3 darts like that. Determine which diagram best represents the following phrases and explain why. So which of these 3 figures is accurate and precise? Well, close to the accepted value, what they're trying to get to. So they're trying to throw it at, throw as many darts as possible in the center. So they're trying to get to, that's the accepted value, the center. So accurate would be how close they are to the center, and precise, they're all together. So figure 2 is the best one for this. They're accurate around, they want to be in the middle, and all 3 are at the middle. Precise, but not accurate. So again, they're not near the accepted value. They're quite away from the middle, but they're all pretty precise. They're all replicated the same. They're all clumped together, so that's figure 1. And neither accurate nor precise. None of these darts are near the middle, and none of them are close to each other, so they couldn't replicate the same accuracy. So we would say that this is figure 3. All right. Last page of notes for today then. Part B, the goal of the dart game has changed. The goal is now to throw as many darts as possible in the striped region of the dartboard. Use a diagram showing to place the 4 darts in such a way so that it illustrates accuracy but not precision. So you want to be accurate but not precise. So the objective is to have it in the striped section. So as long as I put darts anywhere in the striped section, I'm going to be accurate. To not be precise, I don't want them to be all together. All right, so maybe a grouping like that for your 4 darts would be accurate but not precise. Example 10. Aurora sets the temperature of her lab cooler to be 35 degrees Fahrenheit to test a new temperature sensor. She's confirmed that the cooler sensor is working correctly and that the lab cooler maintains a constant temperature of 35.0 degrees Fahrenheit. The new temperature sensor is tested 10 times in the cooler and the results are shown below. Aurora described her measurements as accurate but not precise. Explain why she is correct. Well, the accuracy should be near 35 degrees Celsius, right? And all these measurements are centered around 35 degrees, so we would say that's pretty accurate. So accurate as the measurements are all pretty close to 35 degrees. We would say they're not as precise. Not precise because there is no consistency or poor consistency. You get some that are above, some that are below. We're not very consistent with our measurements, but we are pretty accurate. They're all about 35 degrees. Okay, so you guys have your assignment. You guys can begin. Away you go.